The next unit that we're going to be in is about trigonometry identities and solving and being able to manipulate equations and just kind of solve things using what we learned last chapter. The word identity is something that you've seen before. Like, you have an identity. It's being who or what you are. And things have the same thing. So the fact of being who or what that thing is an identity. So when you say that you have a trig identity, that basically means that you have two expressions, two trigonometry expressions that are always equal to each other no matter what you plug in. And so when we're dealing with this, we're dealing with things that are always equal all the time. And there are some identities that we have to memorize, and then we're going to have problems where we have to use these identities. In order to be good at verifying trig identities, verifying basically is kind of like proving. So just like in geometry when you did some proofs, you're going to do similar things with trig identities. You're going to have to prove that they are true, and we call that verifying in this class. So in order to be good at verifying trig identities, you have to be good at two things. First of all, you have to be good at knowing the memorized trig identities. And the second thing you have to be good at is algebra, because you use a lot of algebra rules in this. Some examples, I'll just list them on the side. Factoring, getting common denominators, using conjugates, another example would be, actually that's enough for right now because we'll talk about it as we move on and go into other notes on the packet. But you have to use algebra, and you have to know what we memorize. So the things that I'm about to say are things that we're going to want to memorize. We break these things into categories to help us understand them a bit better. And so when we look at the first category we're going to talk about are reciprocal identities. And the reciprocal identities are things we actually already know. So for example, we have this graph of a right triangle on the unit circle. We know that sine is opposite over hypotenuse, which is always the y value divided by the radius of the unit of the circle. And then cosecant is that flipped, or the reciprocal of it. And so on and so forth. All of these things we already learned last chapter. So we have to memorize or know that sine of x equals 1 over cosecant of x, and cosecant of x equals 1 divided by sine of x. Basically, all of those things are reciprocal identities. They're always true, so it's an identity, and we know that these are the reciprocals. So I know that if I have sine in the numerator, that's the same thing as cosecant in the denominator. Or if I have sine in the denominator, it's the same thing as cosecant in the numerator. And that works for all of those things. Another thing I'll put in this category, even though it's technically not a reciprocal identity, but it kind of fits in with these, is one thing you may or may not have noticed before is that tangent is y over x, but that's also the same thing as y over r divided by x over r. Now we know that y over r is sine and x over r is cosine. So really, I can write tangent not only as y over x, I can write it as sine over cosine. So I can write tangent as sine over cosine, and I can write cotangent as cosine over sine. These are 8 identities you absolutely have to know, and we're going to use these all the time. Something to keep in mind, and I know we've discussed this before, but the x over here is not the same as the x over here. So when we're talking about x and y on the unit circle, that's not the same thing as when we're referring to sine of x or cosine of x on like a trig function graph or something. So those are not the same x. We're just relating two things that are kind of the same. I also could have done this with any variable I wanted, including the Greek letter theta or something. So I could have said sine of theta equals 1 over cosecant of theta, and so on and so forth for all of these with different variables. But I chose x, and you're just going to have to deal with it. Next, other basic identities called the cofunction or reflection identities. These are all based on our understanding of the unit circle. Some things you may or may not have noticed. Sine of pi over 6 and cosine of pi over 3 are the same thing. Now, pi over 6 and pi over 3, if I change them to degrees, would be 30 and 60. And likewise, the same thing is true for sine and cosine of pi thirds and pi sixths, respectively. This is something that you actually learned in geometry, that if I have a right triangle, I know that the other two angles have to add up to 90, which is the same thing as pi over 2 in radians. And so another thing you always learned is that the sine of A being opposite over hypotenuse for A is going to be the same thing as the cosine of B, because whatever was opposite of A is going to be adjacent to B. So sine and cosine have this relationship where the sine of one angle in a right triangle is equal to the cosine of the other angle in a right triangle. Now, as we extend it to the unit circle, we're not always dealing with, we do draw the right triangle on the coordinate plane, but we don't always think about it in terms of right triangles anymore. But that doesn't mean that it's not still true when we're dealing with angles that are off by 90 degrees from each other. So if I take a look at sine of, remember that pi over 2 is like 90 degrees. If I take 90 degrees and subtract the angle, if I do sine of that angle, I get cosine of that angle. And that is basically what this was saying. The sine of pi over 6 is going to be the same thing as cosine of pi over 2 minus pi over 6, because that is cosine of pi over 3. That's something that has always been true when you were dealing with stuff in geometry with this 90-degree stuff. It's also true when you're dealing with radians or you're just dealing with anything in general on the unit circle. That's why we have sine and cosine, tangent and cotangent, secant and cosecant. These are the cofunction identities. This is how they are related. We also have some other relationships on the unit circle, and I'm just going to put them up and kind of show you why they work. So if we have some sort of angle, I have theta in red and alpha in blue. If I take the negatives of those angles, I can kind of see what's going to happen. Like, I know that sine is positive in the first and second quadrant. So if I have an angle in the first quadrant, its negative will be in the fourth. Well, sine is positive in the first and negative in the fourth. So that means if I have a negative angle, that's the same thing as negative of the positive sine of the positive angle. And that works the same for cosecant. Tangent's going to work the same way. Tangent's positive in first and third. So notice that the red or the blue, it doesn't really matter. One of them is going to be positive and one of them is going to be negative. But what's really interesting is when you look at the cosine of a negative angle is equal to the cosine of the positive angle. So that makes sense because cosine is positive in first and fourth and negative in second and third. So that means that if the red one was positive, the negative red one's also positive. And if the blue one's positive, the negative blue one's also positive. And so on with cosine. And so when you look at sine and tangent, essentially what that means from an algebraic perspective is if you see a negative angle, you can actually turn it into negative of the function of a positive angle. That's true for sine, cosecant, tangent, and cotangent. For cosine, the negative angle actually can just basically go away. We can treat it like the positive angle. So just an example, cosine of 30 degrees is equal to the cosine of negative 30 degrees. But the sine of negative 30 degrees is not equal to the sine of 30 degrees. It's equal to the opposite of the sine of 30 degrees. So those are just some examples. Finally, the Pythagorean identities. These are based on the Pythagorean theorem. So if I look at this right triangle that I drew with x, y, and r, I know that x squared plus y squared equals r squared. Well, what I'm going to do is I'm going to just manipulate this by dividing every term by r squared. So now I have x over r squared plus y over r squared equals 1. We know that x over r is equal to cosine on the unit circle. We know that y over r equals sine on the unit circle. So basically, cosine squared plus sine squared equals 1. This is a huge identity. You will use this all the time. Just like in the Pythagorean theorem in geometry and algebra 1, you use that all the time. We will use the Pythagorean identities all the time. So cosine squared plus sine squared equals 1. One other thing to keep in mind is that cosine theta squared, we will often write as cosine squared of theta. So that's something that is notationally the way that we do it. We put the squared in between the cosine and the theta, and that works for all of the functions. That's just kind of the way that we notationally write it. Now, I only memorize the first one. I don't memorize the other two, but I can very easily get the other two. So here's how I get it. Because I know that sine squared plus cosine squared equals 1, all I have to do is divide by one of either sine squared or cosine squared, and I get the other two identities. So let's say I divide by sine squared. Sine squared over sine squared is equal to 1. Cosine squared over sine squared is cosine divided by sine. Now, if I don't remember what cosine divided by sine is, I need to remember that. That's cotangent. So cosine divided by sine is cotangent. So cosine squared divided by sine squared is cotangent squared. And then 1 divided by sine is cosecant. So 1 divided by sine squared is cosecant squared. So I get this identity by dividing everything by sine. Likewise, if I divided sine squared plus cosine squared equals 1, if I divided that by cosine squared, this becomes 1. Sine squared over cosine squared is tangent squared, and 1 over cosine squared is secant squared. That's how I get the middle one. So I only memorize the first one, but all of them are very important, and you will use them all the time. Now, what do these problems look like? So we talked about verifying trig identities. Verifying basically just means showing that it's true. It's basically a proof. So you can manipulate things, but you can't do typical equation rules like multiplying by both sides or dividing things to both sides or adding or subtracting to both sides. Basically, you can only work with one side at a time, and then you're trying to get one side to look like the other one. So I'll just quickly do 4 examples to kind of show you what it's going to look like. I'm only going to work with the left-hand side in number 1. Now, you can technically work with both sides, but you can't multiply the same thing to both sides or whatever. And we may show an example of that sometime later. So if I'm looking at problem 1, that looks a little confusing. I'm going to work with the left-hand side. What I'm going to do is I'm going to rewrite everything in terms of sines and cosines. That is one of the tricks that we're going to end up using if we don't know what to do. Just write everything in terms of sine and cosine, and that may give us a chance. So cotangent, according to one of the rules I learned earlier today, or if hopefully I knew it already, is cosine x over sine x. And cosecant is the same thing as 1 divided by sine x. So I go from that first original given to now I've rewritten everything in terms of sine and cosine. Now I can use the fact that I have a common denominator of the denominators. So sine x in the denominator of both is going to end up canceling out. Or if that confuses me, then what I can do is I can rewrite dividing by a fraction to multiplying by the reciprocal. So cosine x over sine x times sine x over 1. The signs will end up canceling, and I end up with cosine x. Notice that that's exactly what the right-hand side is. Once I get to the right-hand side, if I've gone from left to right, and I haven't done any multiplying by both sides or whatever, I've shown that the left side equals the right side, and that means that I've won. Whenever I win, I put an X with a box, just because that makes me feel good. Now let's look at problem 2. Manipulating either side might be tough. I will go with the left-hand side. So I'm going to rewrite everything in terms of sine and cosine. So cotangent is cosine divided by sine, and tangent is sine of x over cosine of x. Now, one of the things I'm adding fractions, I'm going to have to get a common denominator. So I'm going to multiply the first term by cosine of x in both the numerator and denominator. Then I'm going to multiply the second term by sine x in both the numerator and denominator. So now I have a common denominator of sine x, cosine x. And then what I'm going to do is I can add these things because they have a common denominator. So I have cosine squared x plus sine squared x all over sine x, cosine x. Well, what is sine squared plus cosine squared? I know that that's 1. So what I can do is I can simplify that to be 1 divided by sine x, cosine x. And then what do I know that sine x in the denominator is? That's cosecant x. What do I know that cosine x in the denominator is? That's secant x. Well, and then I can just use the commutative property of addition or multiplication to get it to look exactly like the right-hand side. So I've just solved another or verified another identity. Now, one of the interesting things is I also could have worked with the right-hand side. If I worked with the right-hand side, what I would have done is I would have started here, rewritten everything in terms of sines and cosines. Then I would have had to make this logical leap that 1 is cosine squared plus sine squared. And then I could manipulate my way back this way. So working with the left-hand side was a lot easier in this problem because I wouldn't have had to take 1 and converted it into cosine squared plus sine squared. It's a lot easier to take cosine squared plus sine squared and convert it into 1. I'm going to work with the left-hand side on number 3. I'm going to convert secant squared into sines and cosines. So I have sine squared x over cosine squared x. And then I have this cosecant squared. I'm also going to convert that into sines and cosines. So now I have sine over cosine, that's tangent, and they were both squared. Sine over sine is just 1. And then tangent squared plus 1 is secant squared, as I learned earlier on this page. So I'm done with this problem. That problem was really not very hard if you convert everything to sines and cosines right away. I actually, if I were doing this and when I first saw this problem, the first thing that I would have done was I would have tried to factor out the sine squareds. And I would have had something like this for my left-hand side now. That actually, I can still convert things into sines and cosines, but then I'd have to distribute the sine squared back out. So that's a lesson that sometimes you don't always get what you want the first time or second time you do something. You might have to manipulate and try things a little bit. The other thing that is kind of important to note when I'm doing these problems is that if I'm looking at it, I want to try and manipulate the harder side and always keep the end in mind. So if I'm looking at secant squared x, my goal is to take the left side, which looks more complicated, and convert it into secant squared. So if that's my goal, that's what I got to try and do. And if I do 1 or 2 steps and it doesn't look like I'm getting myself closer to secant squared, then I need to pack up and try again. Looking at number 4, well, I'll work with the left-hand side again. This is something where I'm going to really have to use my algebra. So 1 minus cosine to the 4th is the same thing as 1 minus cosine squared times 1 plus cosine squared. And the reason that that is true is because it's the difference of two perfect squares. Now, 1 minus cosine squared, I can continue to manipulate 1 minus cosine x, 1 plus cosine x. I don't know if that's actually going to help me though. I mean, I can continue to do that, but I'm looking at the right side and I need everything to be sine. So because I need everything to be sine, that may not be the best option for me. So I'm going to not do this, and I'm going to try something different. So let's look at 1 minus cosine squared. Well, I know that sine squared plus cosine squared equals 1. So what happens if I subtract cosine squared from both sides? Sine squared equals 1 minus cosine squared. So if I look at 1 minus cosine squared, I'm going to rewrite that as sine squared. That helps me because I want to get closer to sine squared. So that's good. Now 1 plus cosine squared, I want to get a bunch of sines. So I'm going to rewrite cosine squared as 1 minus sine squared, which I could also do if I subtracted sine squared to the other side in this equation. So I just rewrote the cosine squared part as 1 minus sine squared. And now all I have to do is do some distributing. So sine squared x, 1 plus 1 is 2. And now I distribute and I get 2 sine squared x minus sine to the 4th x. And I'm done.